Okay, for the last part of chapter 7, we're going to look at colloids and dialysis. So something that's kind of related to medical fields. So first, let's define what a colloid is. And a colloid is a homogeneous mixture, but it's not a solution of two or more substances in which the dispersed substances are found as large particles. All right, so it's a little bit weird to think about, but the classic example of a colloid is imagine pouring homogenized milk from your fridge, right? When you look at it, it's a homogeneous mixture. In fact, it has the word homogenized in the name. However, it's not like a solution where things are clear and dissolved, right? Instead, you've got these itty-bitty fat globules stuck in your milk, and these are a little bit larger than standard dissolved particles in something like a sodium chloride dilution. All right, so let's try to break this up into two parts, kind of like we did for solutions. And the first part is just called the dispersing medium. And the dispersing medium is a lot like a solvent, but it's the term we use when we're describing a colloid versus a solution. And then on the other side, we've got a dispersed phase. And a dispersed phase is a lot like a solute. However, the solute is bigger. All right? It's bigger than our standard solutes, therefore milk is nice and cloudy. However, it's not so big that it'll actually settle out. Therefore, the solution remains homogeneous. All right, so let's go ahead and take a look at kind of a unique property of colloids. And it has to do with light. So if you shine a light through a solution, it doesn't scatter any light. So over here, we could say that solutions do not scatter light, because the particles are just simply too small. The particles typically are less than 0.1 micrometer, versus over here, a colloid, you can see kind of in here that the light is getting scattered. All right, so it's a little bit weird to think about, but the solute in a solution, I said, is smaller than 0.1 micrometer. If we think about the solute for colloids, these typically are bigger than 0.1 micrometers. So they're relatively large, but not so large that they settle out. It's a little bit weird to think about. So let's just make a note here, but not so big that they settle. At least not under normal gravity. You can centrifuge them, which you might talk about in some of your biology courses, but under standard, gravitational conditions, these particles remain suspended, and the colloid looks like a homogeneous mixture. All right, let's go ahead and talk about this next table, which is table 7.7 in your book. I don't know why it always pastes off to the right. But this looks at a handful of different colloids you might be familiar with. So one we just talked about was milk, right? So milk is a liquid colloid. So it's primarily made of water, but you've got a lot of proteins and fats that are essentially homogenized into that water. And this is also called an emulsion. We'll talk about this later, but an emulsion is when you get two unlike things to mix, basically a fat and water in this case to mix. Mayonnaise is also a good example of a colloid. So mayonnaise uses eggs as an emulsifier to form one common mixture, in this case a homogeneous mixture. However, there's quite a few other types of colloids. The main idea with this, though, is they're the same throughout, meaning the same types of particles throughout. They're dispersed evenly, but they're not so big that things separate out into discrete chunks that you could see even with a microscope. So that's the big difference here. All right, so I did want to talk about a couple of other things, and that is that cations and anions tend to surround these colloids. So cations or anions surround colloids and stick to their surfaces. All right, so essentially they help disperse these little itty bitty particles, because if you're surrounded by a shell of anions, right? So let's just imagine this is my itty bitty particle, and I've got a bunch of cations surrounding me. Will this really want to aggregate with another adjacent particle over here? Well, probably not, right? Because this positive-positive interaction is destabilizing. So instead, they'll tend to separate, which is a good thing. It prevents aggregation. So let's add this as a note. So cations and or anions surround colloids and stick to their surfaces. This prevents aggregation. Which is kind of interesting. All right, there's another term I wanted to bring up though, and this is related to the example of mayonnaise I talked about earlier. And these are emulsifying agents. Or they're sometimes referred to as stabilizing agents too, so I'll do both here. And emulsifying and stabilizing agents are substances that are added to colloids to help prevent aggregation. So it's not a part of the original colloid, it's added. To prevent aggregation. So a good example of this is, let's imagine that we have really finely dispersed tiny micro oil droplets, right? Well, what you could do is, if you want to prevent those oil droplets from forming a layer, you could add in something like soap. And so this would be a good example of an emulsifying or stabilizing agent for oil, because this part over here is attracted to oil. And then this part over here has a charge associated with it, so it is attracted to water. Because water is polar, oil is nonpolar. So this is the whole idea with how soap works. All right, so let's talk about one last thing. And this is dialysis through a dialysizing membrane. I always struggle to say that. All right, and this is kind of unique. This is similar to an osmotic membrane. However, it has much larger pores. that are big enough for solvent, ions, and other small molecules. If we think about the osmotic membranes that we talked about before, those were only big enough for solvent. They weren't big enough for ions or other small molecules. Where this one kind of opens up the gate a bit wider so that we can fit small things but not giant things through the pores. All right, and this is the whole idea behind dialysis. Dialysis is a medical procedure, but it's also a scientific one. It is the process through which solvent, usually water, flows over one of these membranes and kind of extracts out all of those smaller things but leaves in the bigger things. Where solvent flows over a dialyzing membrane, causing smaller but not large particles to pass over. Okay, so another way of thinking about this is it leaves those colloid particles behind. So let's take a look at this using a visual. So here's kind of a simple idea. So let's imagine that here we've got this membrane on the outside. So it looks kind of like a hot dog, but this is just a membrane, and it's got pores in it that will allow small things through. So these bigger things, like these large spheres here, they're too big to fit through the pore. However, anything that's small, so for example, these ions and small molecules here, they will all get passed through into the water. So the great thing with this is over time, if you put pure water in and pull water out, some of these small molecules and ions will essentially diffuse out through these pores into that water, and you can just keep on flushing it. This is exactly how things like kidney dialysis works. We want to extract all of the small molecules and ions out of your blood, but we don't want your blood cells and immune cells coming out along with those small molecules. So we have to have membranes where the pores are the appropriate size to leave in all of those good biomolecules and cells without being so big that they accidentally come out. All right, I hope that helps, but let me know if you have any questions.